Hello, my little ninjas. This is your ma'am Akshata, and I welcome you all to the summary session of the most important and interesting chapter, which is acid, bases, and salts. And what all are we trying to cover in our session today? So we shall be learning about acids followed by bases. Then we shall be looking at the indicators followed by the chemical properties of acids and bases. And then we will learn about the classification of acids and bases based on their concentration. We will then look about the dilution of acids and bases. And finally, we will be talking about pH and salts. So we shall start our session with the topic, the nothing but acids. Acids. We have come across the term acids a lot. But where has this term derived from? It has been derived from the Latin term, the Latin word, which is acidus. It is derived from the Latin word which is acidus, which means sour to taste. So acids are sour to taste. The tangy flavor you get when you have the lemon, where is it coming from? It is coming from the citric acid that is present in the lemon. And this citric acid is nothing but an acid. So what do we understand from this? We understand that acids are sour to taste. Then an acid is defined as a substance that releases H plus or hydronium ions. Acid is defined as a substance that releases H plus ions or hydronium ions. But where does it release these ions? Does it release it in the air? No. It releases these H plus ions in their aqueous solution. That is, when an acid is dissolved in water, what it releases is H plus ions. And it is these H plus ions which determine the acidic character of a given substance. And on the basis of the source from where they are obtained, acids are of two types, mineral acids and organic acids. Mineral acids are obtained from rocks and minerals. Example, the hydrochloric acid, the sulfuric acid, the nitric acid, etc. are all examples of mineral acid. And when we talk about organic acids, that is acids that are obtained from organisms, living organisms, that is plants and animals, are known as organic acids. So here are a set of examples for mineral acids, which includes hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid, so on and so forth. And here you can look at the organic acids. Vinegar, which you like in your Manchurian or in your noodles, it happens to have acetic acid. And the sour milk, when the milk gets sour or formation of curd, it happens to have lactic acid. Citrus fruits have citric acids. Your tamarind has tartaric acid. So here are a set of examples for organic acids. All right. Now, the classification of acids is really interesting where based on source we know that it is of two types, that is, it is natural and mineral, and we are already aware of their examples. Now, talking about based on concentration, we will study that in detail in another few minutes. But let me tell you, based on concentration, they are again of two types. They are concentrated acids or dilute acids. Concentrated acids or dilute acids. And then based on ionizing capacity. What is ionizing capacity? The ability of the acids to be able to give rise to H plus ions. To be able to give rise to H plus ions is nothing but its ionizing capacity. So more easily if more easily it can release its H plus ions, then such acids are known as strong acids. And when these acids do not very easily or completely dissociate to give rise to H plus ions, then they are called weak acids. Generally, mineral acids are strong acids, while organic acids are weak acids. And don't you worry about concentrated and dilute acids. About that we will learn in a couple of minutes. Now let's talk about bases. Acids are sour to taste. So what about bases? Bases are bitter to taste. And they are soapy to touch. Bitter gourd is bitter. Why? Because of the presence of a base. In fact, your soaps also happen to contain bases. Do not taste them. Just take my word for it that they are bitter. Alright? So bases are bitter to taste and they are soapy to touch. And some of the bases like sodium hydroxide and potassium hydroxide are corrosive in nature. Now what do you understand by the term corrosive? See, corrosive is if their solution happens to fall on our skin. Alright, if it happens to fall on our skin, then what will it do? It will corrode our skin surface. That is, it will cause a burn. Alright, so that is perhaps the reason why sodium hydroxide is also known as caustic soda, because it is capable of causing burns. Alright, so sodium hydroxide and potassium hydroxide are really strong bases and they are corrosive in nature. And their corrosive action is seen on the skin and can even harm the body. Alright, and a base is defined as a substance that is capable of releasing OH minus ions in aqueous solution. So acids release H plus ions in their aqueous solution, in their aqueous solution, whereas bases release OH minus ions. It releases OH minus ions in the aqueous solution. So this is about acids and bases, a brief introduction of acids and bases. Let's now try to understand a class of bases which is known as alkalis. A class of bases which is known as alkalis. Now what are alkalis? Alkalis are defined as soluble bases. So the bases which easily dissolve in water. Alright, such bases are known as alkalis. Alright, so sodium hydroxide and potassium hydroxide are some examples of water soluble bases, and that is perhaps the reason why they are known as alkalis, so much so that they are also known as alkali metals. Here you can see are some examples of strong bases, which includes sodium hydroxide, potassium hydroxide, barium hydroxide and calcium hydroxide. So this is about acids and bases. Let's now try to see the classification of bases. So based on solubility, we know that a certain few bases are soluble in water, and the ones that are soluble in water, what are they known as? They are known as alkalis. So what about those bases which are not soluble in water? Well, yes, there are a certain few bases which are not soluble in water, and they are not alkalis. alkalis. They are not called alkalis. What is the example of it? Copper oxide. It is a basic oxide. Copper oxide is a basic oxide and it is not a alkali. Now talking about the ionizing capability or ionizing capacity. Just like how acids are strong and weak based on their ionizing capacity. So we know that those acids which very happily or which very easily release H plus ions are called strong acids. Whereas those acids which do not release or which do not completely dissociate to give rise to H plus ions are known as weak acids. Applying the same logic for bases, so bases that release OH minus ions, that is hydroxide ions easily, are known as strong bases. Whereas those bases which do not very easily give rise to or which do not completely dissociate to give rise to the hydroxide ions are known as weak bases. They are known as weak bases. So the example of strong bases is sodium hydroxide, whereas that of weak base is ammonium hydroxide. Of that of weak base is ammonium hydroxide. So now the question here is, all right, there are acids, there are bases, but how do we determine that a given solution to us is an acid or a base? If we do not know, then we will not be able to understand, and we might, what if, pour it on our skin? See, that can cause fatal accidents, right? So how do we know that a given solution that you see, the clear solution that you see, whether it is an acid or just simply water? So there is a way by which we can do that. So the substances which indicate whether a given compound, a given solution is acidic, basic or neutral is known as indicator. Now, how does it indicate whether a given solution is an acid or a base or a neutral solution? Well, based on a certain few changes. If there is a change in color, so based on the change in color, we can determine that, all right, this given set of a solution is an acid or a base or whether it's neutral. But if there is a change in smell, such indicators are known as olfactory indicators. Such indicators are known as olfactory indicators. So here are a certain few. These are the types of indicators that you can see. So an indicator is nothing but a chemical compound that changes its color in the presence of an acid or a base. And indicators are generally derived from plant pigments and are mildly acidic or basic in nature. But when they are derived from plant pigments, they are known as natural indicators. If they are derived from chemical substances, then they are known as synthetic indicators. And here are a set of few examples. The most common natural indicator is red cabbage, all right, and then we also have litmus. All right, then synthetic indicators, we have phenolphthalein, methyl orange. For olfactory indicators, we have onion, vanilla. All right, so these litmus is the most common natural indicator. Now, what is litmus? Litmus basically litmus solution is derived from lichen. All right, it is derived from lichen. Now, the lichens are of different types. Now, based on the different types of lichens, the litmus solution is derived from. It can be red litmus solution or blue litmus solution. So let's look at how the litmus interacts with acid or a base. So here is a set of the table. Now, what we can do is, instead of trying to understand it like this, we have the mnemonic BRB. No, here BRB does not mean be right back. Here BRB stands for base turns red litmus. It turns red litmus to blue. Base turns red litmus to blue, whereas we have ABR, abracadabra. So here A stands for acid, turns blue litmus to red. Alright, acid turns blue litmus to red, and that's exactly what you see over here. We have blue litmus in the presence of an acidic solution, it turns red, whereas there's no change in case of basic or neutral solution. Talking about red litmus solution, there is no change in color in the acidic solution. However, it changes to blue in the presence of a base. Now, talking about methyl orange turns red in acidic solution and yellow in basic solution. And in the neutral solution, it happens to have the orange color. Talking about phenolphthalein, there is no effect of acid. It is colorless. Alright, it turns colorless in acidic solution. It turns red in basic solution. It is colorless in neutral solution. So this is about the indicators. I hope it is clear so far. We shall now look at the chemical properties of acids and bases. Now, how do acids and bases interact? Starting with acids, with metals. Acids react with metals to give rise to salt and hydrogen gas. It forms a salt along with the hydrogen gas. And with respect to this hydrogen gas, we can test for it. How? Now, when we bring a burning matchstick, close to the beaker from where the hydrogen gas is liberated, what happens is the candle or the matchstick, it loses its flame. That is it stops burning with a pop sound when it comes in contact with hydrogen gas. So this is how metals interact with acids. Now what about the reaction of acids with metal oxides? Now, metal oxides are nothing but basic in nature. So, when acids react with metal oxides, what we get is salt and water. Also, when this particular acid, that is sulfuric acid, let's say reacts with NaOH, what we get? NaOH is nothing but a base. What we get is sodium sulfate plus H2O. Sodium sulfate plus H2O. We get sodium sulfate plus H2O. And it is now a balanced reaction. So what do you understand from this? That when an acid reacts with a base, it undergoes neutralization, and what we get is the salt and water. Now, talking about the reaction of metal carbonates with acid. Metal carbonates are also basic in nature, but along with the formation of salt and water, carbon dioxide is also liberated. Alright, so this is about the chemical properties of acids. Let's now talk about the chemical properties of bases. Okay, reaction of bases with metals. Now, when metals react with bases, even in that case, what we get is a salt. Along with the liberation of hydrogen gas. And this hydrogen gas, when it comes in contact with burning candle, it stops its burning with a pop sound. So this is about the chemical properties of bases, where bases react with metals. Now, what happens when bases reacts with non-metal oxide? Now, non-metal oxides are nothing but acidic oxides. So, when a non-metallic oxide interacts with a base, what we get is salt and water, as you can see over here. Sodium hydroxide, when it reacts with carbon dioxide, we get sodium carbonate along with the formation of water. So what kind of a reaction is this? This again is neutralization reaction. Neutralization reaction. What do you understand by the term neutralization? See, acids have an acidic character. Bases have a basic character. Now, when the acidic character of an acid, that is H plus, it is because of H plus. Basic character of a base is because of the OH minus ions. Now, what happens? I'll help you understand what basically neutralization reaction is. I want you to understand what basically neutralization reaction is. Basically, in neutralization reaction, the acidic and the basic character of the acid and the base is lost. Let's see how. We know acid, let's take HCl over here. It dissociates to give rise to H plus and Cl minus ions in its aqueous solution. Okay. Similarly, let's take a base, NaOH. NaOH also in its aqueous solution gives rise to Na plus Cl minus ions. Right? Now what happens? What happens is you will see the Cl minus ions and the Na plus ions combine to give us the salt, which is NaCl. Right? And the acidic character of an acid is because of the H plus ions, and the basic character of a base is because of its OH minus ion. So when this H plus and this OH minus ions come together, what we get is water. Thereby, this reaction is known as neutralization reaction. I hope it's clear till here. Let's now try to understand the classification of acids and bases based on their concentration. Now, what about their concentration, beta? See, what do you understand by the term concentration? Concentration is nothing but, the number of moles of a substance per unit volume, that is in a given volume, let's say liters. This is concentration. Now, how do we classify acids and bases based on concentration? More are the molecules of, see, we know we have acid plus water, right? This is one. And we know there is base with water to form its aqueous solution. We are aware of this, right? When the number of acid molecules is greater than number of water molecules, then it is said to be concentrated. All right. Similarly, for base, when the number of moles of base in a given solution is greater than the number of water molecules, then it is said to be concentrated. All right. Talking about dilute. So what about dilute? Dilute is the reverse. That is the number of moles of acid or the base is less than the number of water molecules. Okay, that is what is understanding of dilute. Okay, so this is about concentrated and dilute. Concentrated is the number of molecules of acid or the base is greater than that of water in its aqueous solution. And with respect to dilution, or with respect to dilute acid or a base, that is the number of acid or base molecules is less than the number of water molecules, in the given solution. So based on this we can categorize concentrated acid, concentrated base, dilute acid, dilute base. Now the thing is, in the laboratories, certain reactions are very, very sensitive. All right. So what we do is we interact, or we make sure that these reactions, and such reactions we use dilute acid or dilute base. Now, how do we do that? So we have concentrated. Let's say you have a concentrated acid. Let's say you have a concentrated acid. All right, and you have to dilute it. The question is, how will you do that? So there are two ways. We know for concentrated acid, the number of moles of acid is more. In case of dilute acid, the number of moles of acid is less. Right? Now what do? We have to ensure that the number of moles of acid decreases. How do we do that? This can be done by the addition of water. But the question is, how do we add this water? Do we add? Now there are two cases. Case one, acid is added to water. All right, and then there is case two, where water is added to acid. All right, let's talk about case two. What happens when water is added to acid? All right, okay, let's take a beaker. Okay, and in this there is acid. This is the acid. To this, what are we doing? We are adding water. To this. Now what happens is, the reaction between water and acid is highly exothermic. It is highly exothermic, and what happens is, when this water comes in contact with the acid, its vapors are released. The vapors of the acid is released, and this vapor, when comes in contact with our hands, can cause, this is nothing but vapor of acid, and it can cause, what can it cause? It can cause severe burns. Okay, so thereby we do not add water to acid. Then what do we do, ma'am? We add acid to water. Let's say this is water. Now to this water, what we do is we add acid. To this water we add acid, and we add it drop by drop. Now what happens is, when you add this acid drop by drop, yes, the reaction is highly exothermic. But what happens is, the water is in excess over here. So it acts as a coolant. To the vapors that are formed, and thereby the vapors formed are cooled down. They are cooled down. Now, as a result of which, no burns are no burns are caused. No burns are caused. That is why acid is added to water and not water to acid. So this is how dilution takes place. This is how dilution takes place, beta. Let's now try to understand about pH. What about pH? Can we quantify, okay, and find the amount of the ions? What ions? H plus or OH minus ions that are present in a given solution. Can we quantify them? Is there a way by which we can quantify them? And can we judge how? Can we judge how the given substance is a strong acid or a weak acid? So with the help of indicators, we understand fine that a given solution is an acid or a base. But in any whichever way, can we identify whether it is a strong acid or a weak acid? No, we cannot. So what do? We use the pH paper. Now, how do we get the pH paper? See, we can do this by making use of universal indicator, which is a mixture of several indicators put together. And this universal indicator shows different colors at different concentrations of hydrogen ions. Okay, more is the concentration, concentrated acid. Less is the concentration, dilute acid. More is the dissociation, strong acid. Less is the dissociation, weak acid. Alright, so scale for measuring hydrogen ion concentration in a solution, okay, called pH was developed. Alright, and the P in the pH stands for potens. It stands for potens in German, which means power. Power of hydrogen, that is, how many hydrogen ions are present. That is what pH talks about. So on the pH scale, we can measure the pH generally from 0 to 14. And as we move from 0 to 14, as the pH increases, as you can see over here, as the pH increases from 0 to 14, the basic nature increases as we move from 0 to 14, and up to 0 to 6, they are known as acids, and from 8 to 14, they are known as bases. pH 7 is for neutral solutions. Alright, pH 7 is for neutral solution. Higher the hydronium ion is nothing but H plus beta. Higher the hydronium ion concentration, lower the pH value, inversely proportional. So more is the H plus ion concentration, lesser is going to be the pH. So acids happen to have lower pH but higher H plus concentration, and based on this, bases happen to have higher pH and lower H plus concentration. So values less than 7 on the pH scale represent acidic solution, and as the pH value increases from 7 to 14, it represents an increase in the OH minus ion, which is nothing but our favorite hydroxide ion, and it is this OH minus ion which determines the basic character, right, in the solution. That is, it increases the strength of the alkali. Generally, paper impregnated with the universal indicator is used for measuring pH, and it is known as pH paper. So this is about pH. And here you can see the various pH values. We happen to like our coffee, we happen to like our milk, but they are acidic in nature. They are acidic in nature. As you can see over here, your soap and bleach, okay, 12, 13, right? So these are nothing but the pH values and the various substances which have this particular pH. Now when we talk about pH, what do we try to understand? The strength of acids and bases. Now we know that the strength of acids and bases depends on what? It depends on the number of H plus ions and OH minus ions produced. So if we take hydrochloric acid and acetic acid of the same concentration, that is, if we take hydrochloric acid and acetic acid of same concentration, that is, the number of molecules of hydrochloric acid and acetic acid in a given solution. Let's say we have taken 1 liter, okay, two vessels. Let's take 2 vessels, and let's not take 1 liter, let's take 100 ml, okay, 100 ml water. In both these solutions, I have added 5 molecules of HCl in one and 5 molecules of acetic acid in the other. Then these produce different amounts of hydrogen ions. Why, ma'am? Why do they produce different hydrogen ions? As I've already told you, when you talk about strength, we have to understand that strong acids are the ones which easily let go of H plus ions, which easily release their H plus ion, dissociate to give rise to their H plus ions. Whereas weak acids, they do not easily dissociate to give rise to their H plus ions. So what about them? So the thing that we are trying to understand is mineral acids are generally strong acids and organic acids are generally weak acids. In this case, acetic acid, though happens to have the same number as that of HCl, its dissociation, however, is not similar to that of HCl, because HCl is a mineral acid, and moreover, because of this, it is a strong acid. Alright, so what happens? Acids that give rise to more H plus ions are said to be strong acids, and acids that give rise to less H plus ions are said to be weak acids. Alright, now what is the importance of pH in our everyday life, ma'am? Why are we learning about pH so much? Why are we learning about acids and bases so much? See, acids and bases, we are learning about them because we come across them in our day-to-day lives. How, ma'am? Let's see. So, are plants and animals pH sensitive? Yes, plants and animals are a highly pH sensitive. Our body works within the pH range of 7 to 7.8. Living organisms can survive only in a narrow range of pH. Okay, so when pH of rainwater is less than 5.6, it is called acid rain. So when acid rain flows into the rivers, it lowers the pH of the river water. So the survival of aquatic life in such river becomes difficult. So ma'am, what do we do? See, the pH is decreasing. So what do we have to do? We have to increase it to its normal value. How can we do that? By adding base. Because it has turned acidic. Only if we add a base, what will happen? Its pH will increase, right? That is why here are the various pH ranges in which the various organs of our body function at. And now, what is the pH? What is the pH of the soil in your backyard? So what happens is plants also require a very specific pH range for their healthy growth. What kind of pH do they like? Slightly acidic to neutral soil is said to be ideal for plants. So now if the plants, like if let's say there's acid rain, now because of acid rain, what has happened? The soil has become highly acidic. See, it needs to be slightly acidic or neutral. It is highly acidic. Now what do? We have to increase its pH. So that it is slightly acidic. Instead of it being 0 or 1, we have to bring it closer to 4 or 5. Okay, 5 or 6. Then what do? We add base and we increase the pH. However, if a lot of fertilizers are added, okay, phosphorus is added, zinc is added, copper is added, then it will move. The pH will move slightly towards the alkaline side. Now what do? It has increased the pH, but we need slightly acidic or neutral condition, which is 7. So what do? We will add acids to it and try to decrease the pH and bring it closer to neutral. Alright, so this is how we maintain the pH balance if there is an imbalance. Similarly, with our digestive system, we all like to have chocolates. Come on, let's not lie about that. We like our chocolates, we like our waffles. There are so many things that we like to have. Our pakoras, Manchurian, pizzas, burgers. But what is common in all of these? They are oily. Okay, now oily food generally increases the acidic content in our stomach, thereby decreasing its pH. As a result, what happens? We have acidity. There is this problem. What it leads to the problem? That is nothing but acidity. So now the acidic content in our stomach has increased. So what do? We'll have to neutralize this acidic content, right? How do we do that? By adding base. And what base do we use? We use antacids. That is, antacids are nothing but anti-to acids. Antacids are nothing but anti to acids. They neutralize the excess acid. Magnesium hydroxide, that is milk of magnesia, a mild base, is often used as an antacid. Ma'am, but why do we have to do this? Acidity. Well, acidity causes irritability, burning sensation in your stomach. That is why it happens either due to overeating or excessive oily food consumption. Then talking about tooth decay, very common. We all like to have our sweets, chocolates, do we not? But not everybody brushes their tooth at night and sleeps. Now what happens because of this? When you have a lot of sweet content, okay, so what happens is the tooth decay starts and the pH of the mouth is lower than 5.5. Now what happens is when you happen to have these sweets, okay, what happens is it decreases the pH. Okay, it takes it below 5.5, and as a result of which the tooth enamel which is there, which is made up of calcium hydroxyapatite, which is a crystalline form of calcium phosphate, and it is the hardest substance in our body, it starts to get degraded. It starts to get degraded by the action of bacteria present in our mouth. So what do? That is why it is suggested that brush your teeth before you sleep, or brush your teeth after you consume something sweet. Why? Because toothpastes have base. They have bases in them. All right. Another thing, that is self-defense by animals and plants through chemical warfare. You are aware of bee sting. Has anyone of you ever been stung by a bee? Well, what happens when you get stung by a bee? You see that there is inflammation, there's irritability in that area. Why? Because this bee sting releases an acid which causes pain and irritation. Now, usage of mild base like baking soda on this tongue area gives relief. So what do? We take mild soda like baking soda and rub it on our skin. In fact, nettle leaves also inject methanoic acid, causing burning pain. So what do in that case? We again rub some mild base like baking soda. So this is about importance of pH in our everyday life. So we have discussed about acids, bases, pH, their importance. Let's now talk about the most important aspect of our chapter, which is salts. Can you imagine your food without salt? See, no salt in the food makes it bland, and too much salt makes it salty. But without salt, can we imagine our food? No, we cannot. Salt is highly important for enhancing the taste of whatever we like to eat. Now, where is the salt coming from? When an acid reacts with a base, what we get is salt and water. It is this salt that we are talking about which we shall discuss in detail. So salts are the ionic compounds which are produced after the neutralization reaction between acid and a base. And salts are electrically neutral in their solid form, in their solid or crystalline form. However, in their molten or aqueous form, they are electrically very, very active. So then there are number of salts, but sodium chloride is the most common among them, and that is why it is known as common salt. And it is this sodium chloride which enhances the taste of the food. Now, what are the characteristics of salt? Salts are crystalline solids. They are transparent or opaque. Okay, they are soluble in water. They conduct electricity in their molten state. Okay, and it is not necessary that salt be salty. It can be sour, sweet, bitter, umami. It can have various different tastes, and it can also be odorless. And salts can be colorless or colored. Not talking about the taste. See, I want you to understand that salts are again of three types. Salts are again of three types. The first one is an acidic salt. Acidic salt? Ma'am, but salts are formed upon neutralization. Don't you worry, I'll help you understand about them. Then we will talk about basic salts. And finally, we will talk about neutral salts. Neutral salts. Now, what is it? What is it with acidic salts? Acidic salts. Please clearly understand, when a strong acid interacts with a weak base, the salt that we get is a acidic salt. Example for this can be the interaction between HCl with ammonium hydroxide. What we get is NH4Cl plus H2O. Ammonium chloride is a acidic, it is a acidic salt. Now, with respect to basic salt, now let's try to understand basic salt. So, when a strong base interacts with a weak acid, what we get is a basic salt. Example for this can be when acetic acid CH3COOH, which is a weak acid, interacts with sodium hydroxide. What we get is sodium acetate plus H2O. So this is about basic salts. Talking about neutral salts, that is when a strong acid combines with a strong base or weak acid combines with a weak base. What we get is a neutral salt. Okay, what we get is a neutral salt, and the example for this can be NaCl, ammonium acetate, etc. These are all examples of the various types of salts. Now, I want you to understand one thing. Ma'am, how was this happening? You must be wondering, ma'am, how is this really happening? Let me help you understand. let's say it's winters. Now in winters we like to have bath with lukewarm water, right? So what do? We turn on our geyser and we fill our buckets with hot water, half the bucket with hot water and half the bucket with cold water, and what we get is lukewarm water. But what if we fill more than half the bucket with hot water and some amount of with it cold water? Now will it be lukewarm? No, it will not. It will be more towards the hotter side. Another case is when we fill more than half the bucket with cold water and add some amount of hot water to it. Will it be lukewarm? No. It will be more towards the colder side. What do we understand by this? More is the strength, or more is the degree of hotness or coldness that will determine the kind of water you're taking bath with. Excuse me. Similarly, depending upon the degree of strength, stronger the acid, weaker the base. So it is the characteristic of the acid that will overpass, which will supersede the characteristic of base. We will get a salt, but it will be acidic in nature. Alright. Now, if it is a base which is stronger and the acid is weaker, then the characteristic of the base, the properties of the base will supersede the properties of the acid. We will get a salt, but it will be basic. However, if the strength of acid and the base is same, that is if both of them are strong or both of them are weak, then what we will get is a neutral salt. I hope it is clear. So let's now learn a little about sodium chloride. This sodium chloride is also known as common salt or table salt. And it is formed after the reaction between sodium hydroxide and hydrochloric acid. We already know this, and it is a neutral salt, right? I hope you know why it is a neutral salt, because sodium hydroxide is a strong base. It interacts with a strong acid, which is hydrochloric acid, and what we get is sodium chloride plus water. Clear? Now the pH value of sodium chloride is about 7, because it is neutral. And sodium chloride is used to enhance the taste of the food. Now this sodium chloride is used in the manufacturing of many chemicals. It's not just limited to it being our table salt which enhances our taste. No. It also is used in the manufacturing of various chemicals. Let's see how. Starting with sodium hydroxide. Yes, we can get sodium hydroxide from the NaCl. How does that happen? This process is known as chloralkali process. Why is it called chloralkali? Because in the resultant, in the product side, chlorine gas is formed and an alkali, that is sodium hydroxide, is formed. We all know what an alkali is. Alkalis are those substances, those bases which are soluble in water. Thereby, this is known as a chloralkali process. Now, what basically happens over here? We take the aqueous solution of NaCl, and we subject it to electrolytic decomposition. We already know decomposition reaction. We know decomposition reaction. That is the given substance breaks down to give rise to its constituents. So here we are getting this sodium chloride, which is also known as brine solution, is subjected to electrolytic decomposition, and as a result of which what we get is sodium hydroxide and chlorine gas. And this chlorine is obtained at the anode and hydrogen gas is obtained at the cathode. Alright, and this process is known as chloralkali process. Hydrogen gas, however, is a byproduct. So this is about sodium hydroxide, and we already know why sodium hydroxide is known as caustic soda, because it causes severe burns. Let's now look at the use of the products after the electrolytic decomposition of brine. That is nothing but electrolysis. So this hydrogen gas is used as a fuel, as a margarine, okay, in making of ammonia for fertilizers. Chlorine, on the other hand, as chlorofluorocarbon, pesticides. It is used in disinfectants, okay, bleaching powder, about which we shall learn now. And then sodium hydroxide is used for degreasing of metals, manufacturing of paper, soap, detergents, so on and so forth. Talking about bleaching powder, that is when calcium hydroxide, that is nothing but our slaked lime or lime water, is interacted with chlorine gas. What we get is the bleaching powder along with water. This chlorine gas is obtained from where, beta? The chloralkali process. It is then interacted with calcium hydroxide, and what do we get? We get bleaching powder. Alright, it is also known as chloride of lime, and it is a yellowish white solid. It is a yellowish white solid, and it can be easily identified by the strong smell of chlorine. Chlorine has a very strong smell. When you go close to the swimming pool, you can smell that smell. There's a weird smell. What is that smell? That smell is of chlorine. And when this calcium hydroxide reacts with chlorine, it gives rise to calcium oxychloride, which is nothing but our bleaching powder, along with the formation of water. And this bleaching powder is often used in oxidation reactions. Okay, it is often used in oxidation reactions. And what are the other uses of bleaching powder? So it is a disinfectant, okay, to clean water. It is used as a bleaching agent, okay, in industry and textile industry. It is also used as a bleaching agent in the cosmetics. Talking about baking soda. Why is it called baking soda? Baking soda is another important product which can be obtained by the byproducts of chloralkali process. So in the chemical name of baking soda is nothing but sodium hydrogen carbonate. It is also known as sodium bicarbonate. It has various other names, the bread soda, cooking soda. You must have seen your mother ask you to get some amount of baking soda to make the pakoras that you like in the rainy season. Now these pakoras, in this they add the baking soda. Why? It helps in the rising. Okay, it helps in the rising of the dough. Okay, rising of the batter or dough. But then again, they only add a pinch of it. Not more. Why? Because it has a bitter aftertaste. Why does it have a bitter aftertaste? I shall help you understand that. But let's first understand how it is prepared. When carbon dioxide and water is passed over ammonia and sodium chloride, what we get is the baking soda. Now when this baking soda is subjected to heat, it gives rise to sodium carbonate, and that has a bitter taste. Talking about uses of baking soda, it has multiple uses. It is used in the making of baking powder. It is used in, making the batter of soft and spongy. It is used as an antacid, present in the toothpaste, cleaning agent of ornaments. All right. And since sodium hydrogen carbonate gives carbon dioxide and sodium oxide on strong heating, it is used as a fire extinguisher. Now what happens? What is baking powder? Baking powder produces carbon dioxide on heating. So it is used in the cooking to make the batter spongy. Although the baking soda also produces carbon dioxide in heating, but is not used in cooking because the heating and baking produces sodium carbonate, and it is this sodium carbonate which is bitter to taste. This is bitter to taste. So how do we get the baking powder? What we do is, to this mixture of baking soda, we add mild edible acid, which is nothing but tartaric acid, and it is used with baking soda to make baking powder. So sodium tartarate is nothing but baking powder. And looking at washing soda, as the name itself is suggesting, it is used in washing, and the chemical name of this is washing soda is sodium carbonate. It's sodium carbonate decahydrate because it has 10 water molecules. Now, what is decahydrate? I'll help you understand that. So, you have seen about that sodium carbonate can be obtained by heating of baking soda. That is when baking soda is subjected to heating, what we get is sodium carbonate along with water. Okay, along with water. And this is also a basic salt. What is its use? Washing, used for cleaning. Okay, it is used for making detergent, cakes and powders. It is used for removing permanent hardness of water, and it is used in glass and paper industries. These are its uses. Talking about, you must have seen the decahydrate. What is that? That is nothing but water of crystallization. See, many salts, okay. So many salts contain water molecule and are known as hydrated salts. They contain water molecule. And they are known as hydrated salts. Now this water molecule present in the salt is known as water of crystallization. Now this water molecule is nothing but present in the lattice of that particular crystal. And it is because of this water that the salts get their beautiful color. With respect to copper sulfate pentahydrate. Copper sulfate pentahydrate has its blue color, beautiful blue color, because of the presence of the five molecules of water in its lattice. Okay, however, when we heat it, this 5 molecules of water is evaporated, and what we then get is a gray white colored copper sulfate. Okay, however, upon adding water to this anhydrous copper sulfate, we again get blue copper sulfate. Anhydrous, that is without water. Another example is ferrous sulfate dot 7H2O. It has a beautiful green color. However, when subjected to heating, this water is evaporated and it loses its green color. So with this, my kids, we have finally completed and have understood acid, bases and salts. And with this, I would like to thank you for being a part of this session. I hope it has helped you understand acid, bases and salts better. I shall see you in the next summary session. Until then, keep laughing, keep smiling, keep revising. Bye-bye.